So today's topic is going to be about Lidar data. And this is a data set that I'm really excited to finally share with some of you. This, what you see here, is an example of some of the research work that I've been doing over the past year, which is to take Lidar data and transform that into 3D models of urban fabrics and cities. So you can do this too. And what we're going to show you guys today is how you can download Lidar data, how do you process it and compile it together, and then what kind of outputs you can produce from that. So the first thing is basically, where do you get your Lidar data from? We've gone to this website many times already. Went to this website for DEMs, agricultural imagery. You can also get Lidar data from this site as well. And the process is the same exact process that I've shown you already, where you just select an area, but this time you choose this elevation source data here, then make sure Lidar point cloud is checked, and then that basically allows you to download tiles of Lidar data sets. But the website that I want to share with you today is a different website. This is Lidar data that's specifically focused on the coastal regions of the United States. And so you can see these are the types of data you can find here, but we're going to click on this one called Elevation Lidar, and it brings up a little preview of all the areas in the US where they have Lidar data for. And so basically what you do is you zoom into the area that you want to download data for. You click on the draw button in the upper left corner of the window there and just draw a boundary around the area that, say, New Orleans. And then on the right side, there's a bunch of data sets that you can browse through and look at. The data set that I downloaded for today's tutorial is going to be this one right here, USGS Lidar Upper Plain Delta, and the one that has 7 billion points. Click on bulk download and it goes to this website here. You can see all these LAZ files. You download this thing called this tile index right here, this shapefile. And if you download that, if you go into GIS, this here shapefile that you extract from that website, so you bring that in and you see, you basically get this tile data set of all the Lidar tiles. So I zoom in here, and basically what I did and what you can do if you want to download a Lidar data set tile is just click on one of the squares, then it gives you that link for that tile. And so it's as easy as just clicking that link and it just downloads it directly to your computer. So that's one way to download a tile. Another way that might be a little bit more organized, let's say you want to download a lot of tiles at once, you can just select a bunch of tiles, and then I open the attribute table, and then in the attribute table you can choose this button at the bottom left of the attribute table that says show selected records, and these are all the tiles that you selected manually. So now basically you can just go through here and just click on these and download them one by one. First, let me go to the folder where I save this information into. So let me go back to here. So basically, when you download a tile, it comes in as this .laz file you see here. This is basically a compressed version of a Lidar tile, basically. You need to use a tool in ArcMap called Convert LAS. It's Convert LAS tool. Allows you to click on one of the .laz files. I'll just click one at the top, for instance, and then you choose a target folder where you want to save the extracted data. And then all these other options you just leave as is. Then if you hit run, what you should hopefully get, you should see something that looks like this. This is what you get, is one tile of Lidar data. At a faraway zoom, it just shows up as a red square, but if you zoom into it and eventually zoom in closer, what you should see now is all these points show up. Now, this is only one tile, so we need a way to be able to do a lot of tiles really quickly all together. A technique you should learn how to do is this thing called batch processing. This allows you to do a lot of geoprocesses at once without having to do one by one by one by one. So what I'm going to do is right here, convert LAS. It's still in my geoprocessing window here. If you right click on that, there's this little button called batch. And this allows you to turn that tool into a batch process. So I click on that, and then I just basically leave all this stuff as is. Don't mess with that. Then just click next. And now what you can do is in the batch input LAS, you can click on that folder and you can go into the location where you save the data, and you can shift select a lot of tiles at once. And basically what you do is you click OK, it adds all those tiles in. And then again, you choose a target folder for wherever you want this to be saved. And then everything else you basically leave the same, then just hit run. And then when you finish that process, you should see this, a bunch of .las files. So now you've extracted all these tiles, and now you need to take all these tiles and you need to stitch them together because you want to create one big Lidar data set. use a tool called Create LAS Dataset. So I type in Create LAS. There's a tool called Create LAS Dataset. So I choose that. And then in input files here, you just choose all of those extracted tiles. And then Control A and select all of them. Click OK. And then scroll down here, and then in output LAS dataset, give this thing a name. I'll just call this one for now NOAA demo LAS dataset, and make sure that it has the LAS dataset extension, which is .lasd right there. It should come in automatically, but just in case it isn't there, that's what you need. You need the extension. And then everything else, basically leave as is for now. Make sure this compute statistics checkbox is checked, then choose run. And now you've taken all those tiles and now you've stitched them together. This data set here, it's great. It's fine. You know, if you zoom into this, it's just points. Points will eventually render and show up. You can see like it has all the elevation data and the building heights and everything. We need to convert this data set into a raster format such as a DEM, the file format that you've seen many, many times already. There's a tool called LAS Dataset to Raster right here. So now we take these merged LAS tiles and we convert them to a raster. What we do is in this LAS dataset to raster, in this line here, we'll just choose the LASD file that you created. In the output raster right there, you choose a location. So I'll go in here, the browser, go to folders, go to, I'll just use this folder for now. Then you give it a name. So I'll call this one NOAA Lidar demo. And then you give it an extension for a raster. So .tiff. And then all this other information, you should just basically leave as is. There is cell size right here. This one's important because this number right here underneath cell size basically represents how big the pixel of the final raster is going to be. And the pixel size is going to be based on the units of the data set that is currently being used right now. So most LAS datasets are usually in meters. Let's just put a number in, let's say like 5 or something, and then hit run. And okay, so here you see this thing, this raster data set failed right here. All right, here's what you do to fix this. If this ever comes up where it fails, what essentially is happening is that the coordinate system for this data set needs to be changed. Go into geoprocessing window, another process, type in a tool called define projection, and then you choose the LAS dataset. And then in the coordinate system here, basically just choose a coordinate system that is, let's say, the NAD 1983 coordinate system for the area that you are working in. I'm going to choose this one, as in a south in meters, only because I know the units of this dataset are in meters. So we're going to use that one. And then in define projection, once you have that set up, just choose run. And you see basically it almost looks like nothing changed, but now you can go back into LAS dataset to raster, choose that again, output raster, we'll give it a name again, lidar demo.tiff. Cell size, we'll make it 5 for now. And now if you choose run, it now works. I've already created it. It is this one right here, NOAA Lidar 2017 DSM. At the end of that process, that's the result that you get. That is saved in box right here. Bring that in. This is what you get. So I'm going to zoom into this, and you can see we've taken that point cloud data set and now we turn it into a continuous surface. Think of it as if you take a vacuum sealer and you vacuum seal the planet Earth. This is what you get: topographic surface of the urban fabric, building heights, highway interchanges, trees, power lines. You can see power lines through the city as well. Over the years of me playing with this information, I've eventually found a way to take this and turn it into this kind of information, like here, 3D city models. You're looking at this and thinking, okay, what kind of things can you visualize with this type of data? This is a raster data set, so you can just simply go on the raster symbology options. So I'll just click on that right there. In color scheme, you can choose any one of your favorite ramps that you've hopefully have been creating yourself. You can visualize it in that sense. So this is cool, but one thing that I wanted to show you guys as one potential use of this is to create sun and shade analysis plans of the urban fabric. Imagine you have this information here, this elevation data set, and you want to say, all right, at this particular time of year and this particular time of day, where do the shadows fall? I am going to bring up Helena's board. We're going to use this sun path diagram here, and we're going to figure out some information that we're going to use for this geoprocess. But let's say, you want to get the sun information for something close to, right now we're in September. So we'll just use this line here as an example. And we want to say September at 10 a.m., right? So basically we'll follow that line there. And then we'll go to that position right there as kind of like our marker for 10 a.m. on September. And then you use the azimuth circle to kind of get roughly the azimuth angle. And then we need to find the altitude angle. This is where we follow beep boop 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 meow 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 meow. So now keep that in mind. We will go back to GIS and we're going to use in the geoprocessing window the Hillshade. So I'm going to type in Hillshade. In input raster, we'll choose that DSM. And output raster, we'll save it in here and we'll just call this NOAA Lidar DSM Hillshade. And it'd be nice to put the date and time. So we'll just say August 10 a.m. And then right here, azimuth and altitude. So that's where those numbers come into play. Check this box, model shadows. So hit run. There you go. You have now a 10 a.m. morning sun. We can visualize this on top of the DSM. So, click on that data set there, choose raster layer blend. Let's choose that overlay option, that Photoshop style overlay. You can choose ground points only and export out a bare earth terrain. So if I choose the LASD file, then go to LAS Dataset tab at the top, right here at LAS points. If I choose ground, I just click this drop down arrow and then choose ground. What it does is eventually will show up. It basically removes all points that are associated with buildings or highways or bridges or power lines or trees, and only keeps the points that hit the actual bare earth. You take this, once you put the filter on, you run that LAS dataset to raster function to this, and you will be able to get something that looks like this. You can see what happens is that everywhere where there is no points, it just kind of interpolates in between the points surrounding the building footprint. There's some areas like the water right here that did not interpolate correctly. But if you are, working on a site and you just want the topo for that area, this works great. Then just use the contouring tools. So go to geoprocessing, type in contour, input raster, we'll choose the ground output feature class. I'll just leave that as is for now. In contour interval, we'll choose 1 for 1 foot. And then in Z factor, put in 3.28084. There are 3.28084 feet in 1 meter. And then choose in environments, choose in the processing extent menu there, choose current display extent, and then choose run. You get contours for at 1 foot intervals for that area. So I'm going to go back to my browser, and now we're going to go all the way to the top right here. This data set here, I feel like it was fate that we chose New Orleans, and fate have given us this data set here that we can use to model bathymetry of this New Orleans region. 2022, published on May 31st of 2022. That was recently. And in here, you have all these TIFF files of TopoBathymetry at a very high resolution, 1 meter resolution for that whole area. And what you would do is basically you download that zip file. And again, that zip file right here is already in the box. It's right there. TopoBathymetry DM 1 meter. And in this case, I have uploaded a zip file of several tiles from there. And this is the file that's 1.6 gigabytes in size. If you download those tiles, they look like this. And I'm just bring a few in just to show you what it looks like. These tiles have the bathymetry of the Mississippi River. It has the bathymetry of the lake to the north, Lake Pontchartrain. There's a lot of good information topo-wise of the wetlands in the area. So it's a very comprehensive topographic data set. But basically what I would recommend everyone do is once you download this information here, follow the Mosaic to New Raster tutorial that I showed you in week 1 of Graphic Studies 2. So just go back to the week 1 video, search for Mosaic to New Raster. When you do that tool, you get TopoBathy DM 1 meter. This is what you get. Click on the symbology. Let's zoom into this dynamic range adjustment tool. And then in stretch type, I'm going to choose this histogram equalize option just so that it gets a little bit more detailed. But what's really cool about this, again, if I zoom into the Mississippi River, now you actually get the bottom of the Mississippi. So we actually can map and understand the actual river bed. And there's also some information for the lake to the north. It appears to be some, I'm not sure what this stuff here is. That looks like noise to me. So that might need to be looked into. I don't think this is real. But what's really cool about this, let me change the symbology to a more colorful one. You can see that things like the canals of New Orleans show up and read very clearly. What I recommend you guys do as well is to create a hillshade for this. You can go into the imagery, raster functions, and then at the base of raster functions, I'll open that. There's a hillshade thing right there. Choose that. And then we'll bring in the TopoBathymetry right there. I just leave these as the default. Create new layer. And look at that. Dang. Now you can literally see the base of the Mississippi River. So we have been blessed. We chose New Orleans, and I think New Orleans chose us. So with this hillshade here, you can, again, same thing, raster layer, go to layer blend, let's say use overlay, and now you can overlay that on top of the bathymetry layers. I have given you some data set to play with in the box folder. You download those, use them for Studio. Thanks, everyone. Thanks, everyone. And I hope you all have a good day. Thanks, everyone. Bye.